Hi, in this video, we are going to look at a section on complex numbers. So complex numbers are an important part of the Olympiad syllabus because they have a lot of applications in algebra, sometimes in geometry as well. So what we'll do is we'll go through the theory of complex numbers through problems. The theory is pretty standard, so you will find it in normal textbooks. We will discover whatever techniques that we need for problem solving in this topic, and we'll discover that through questions. So let's start with the first one. So the question is, suppose complex number z satisfies z square plus 2z is equal to z conjugate and not equal to z, right? We have to find the product of all possible values of z, all possible values of z. We start off with an easy one. Here we are just going to use this condition. If z is equal to a plus bi, z conjugate is basically a minus bi, and z square is a square minus b square plus 2abi. And we just put this data in this equation, the given equation. So we'll end up with two equations. A square minus b square plus a equal to 0 and 2ab plus 3b equal to 0. How do I end up with this? I put z square as this, 2z will be 2a plus 2bi, and z conjugate will be on the other side. And when you equate two complex numbers, you have to equate both their real and imaginary parts. Now from here, we can deduce that b comma 2a plus 3 is equal to 0 and b is not equal to 0 because z is not equal to z conjugate. That is given in the problem. Therefore, b cannot be 0. The complex number cannot be a purely real number, right? So therefore, you get a is equal to minus 3 by 2. And once you get a is minus 3 by 2, you can put that in this equation and solve for the possible values of b. And b will come out to be plus minus root 3 by 2. So therefore, the two complex numbers are minus 3 by 2 plus root 3 by 2i and minus 3 by 2 minus root 3 by 2i. And the product of these two numbers is basically equal to 3. So pretty simple question. Here we learned about the normal standard representation of complex numbers and basic properties of conjugate and all, and how to do basic operations like multiplication of complex numbers. Let's look at the next one. Suppose n is less than equal to 1999 with n belonging to natural numbers, and there exists a theta satisfying sine theta plus I cos theta whole power n is equal to sine of n theta plus I cos of n theta. What we have to find is the total number of n that is possible. How many different values of n are there for which this identity is true, right? So this question tells us about something called De Moivre's theorem. So De Moivre's theorem is basically cos theta plus I sin theta whole power n is equal to cos n theta plus I sin n theta. So how will we use that here? We see that sin theta plus I cos theta can be written as cos of pi by 2 minus theta plus I sin of pi by 2 minus theta. And we have whole thing to the power n. So that will become, by De Moivre's theorem, cos of n pi by 2 minus n theta plus I sin of n pi by 2 minus n theta. And since that is equal to sin n theta plus I cos n theta, we can equate the real parts and the imaginary parts now. So we have basically this is equal to this. So we can say 2k pi plus n pi by 2, or you can do it in the other way. So here we can say this is cos. So cos n pi by 2 minus n theta should be equal to sine n theta, which is cos n pi by 2 minus n theta, right? Sine n theta plus I cos n theta is equal to this. So we can just write it as sine of n theta, right? We are equating the two real parts and the imaginary parts. Now this will be true. This can be written as cos of pi by 2 minus n theta. Yeah, that is what I wanted to do. I have converted it into a equation of causes. Two causes are equal. So that will happen if the difference between the angles is 2k pi, right? So we can say 2k pi plus pi by 2 minus n theta should be equal to n pi by 2 minus n theta. So from here n theta gets cancelled and you get 2k plus half is equal to n by 2, which implies n is equal to 4k plus 1. A similar condition will come for the other imaginary part equation also. You can try the same thing. You will get n is equal to 4k plus 1 there. So since n goes from 1 to 1999, 1 is less than equal to n is less than equal to 1999, we will have 0 should be less than equal to k is less than equal to 499.5. Because n is 4k plus 1, you can just solve it and you will get k's interval like this. So the number of values of k, integer values of k are from 0 to 499. So basically the total number of possible values is 500. So that is the answer for this one. Let's look at another one. Here basically we learned De Moivre's theorem. So we'll look at other properties. The third one is this. Suppose two complex numbers, z1 and z2 satisfy mod of z1 is equal to 2, mod of z2 is equal to 3, and 3z1 minus 2z2 is equal to 2 minus I. We have to find the value of z1, z2, the product of the two complex numbers z1, z2. Now, the property that we'll use here is mod of z1 whole square is equal to z1 into z1 conjugate. Therefore, we have z1 into z1 conjugate is equal to mod of z1 whole square is given. That is 2, so 2 square is 4. And similarly, you have z2 into z2 conjugate is equal to 9. This is the standard property that we are utilizing here. So basically, what we can say is 3z1 minus 2z2 can be written as 1 by 3 into 9z1 minus 1 by 2 into 4z2. Why am I writing 9 and 4? Because 9 will be z1 into z1 conjugate. 1 by 3 into z1 conjugate z1 minus 1 by 2 into z2 conjugate and z2. Right? I'm using the fact that this and this are there. So now I can take something common here between these two. I can, one second, let me just see. 3z1 minus 2z2 was given. So, okay, since I cannot take anything common in between these, so that means I made some mistake here. So I will rethink my step here. Okay. I want to find the value of z1, z2. I need a z1, z2 here somehow. And similarly a z1, z2 here, right? So let's think of how we can get that, right? So 3z1 minus 2z2 is given. We know 9 is equal to this. So 3 is equal to what? Z2 conjugate by 3, right? So 3, instead of 3, I'll write Z2 conjugate by 3 multiplied by Z1 minus, instead of 2, I will write Z1 conjugate by 2 multiplied by Z2. Now you can see that you can take Z1, Z2 common from both. If you take Z1, Z2 common, you will end up with, you can take by 6 common also, and you will end up with 2Z. 2z2 conjugate minus 3z1 conjugate inside, right? Now they have told us this value. This value is given to us. So that is 2 minus I is equal to z1 z2 by 6 2z2 conjugate minus 3z1 conjugate, right? So actually, I should not write 2 minus I at this stage. What I can do is I will write 3z1 minus 2z2 itself. And I will say this implies z1, z2 is equal to 6 times 3z1 minus 2z2 by 2z2 conjugate minus 3z1 conjugate, right? So if you take the minus from here, it will become minus 6 times 3z1 minus 2z2 divided by, this will become 3z1 conjugate minus 2z2 conjugate. So now you can see that the top part is a complex number and the denominator is the conjugate of that complex number, right? So therefore, z1, z2 is equal to 6 times. The top part we already know the complex number is 2 minus I. So 2 minus I. And denominator, and there is a minus 6 actually. Denominator is the conjugate of 2 minus I. So that is 2 plus I. So now we'll simplify it by rationalizing, or not rationalizing, we'll multiply it by 2 minus I up and down. We will get minus 6 by 4 square minus I square, so 5. And on top, we'll get 2 minus I whole square, right? So finally, you're getting z1, z2 is equal to minus 18 by 5 plus 24 by 5 into I. After evaluating this, you'll get this. So what was the idea that we used? We used this property, mod z1 square is z1, z1 conjugate. And we use the fact that 3z1 minus 2z2 can be written like this. Because 3 can be written as z2, z2 conjugate by 3. And 2 can be written as z1, z1 conjugate by 2, right? Therefore, we were able to take z1, z2 common here. And after that, it was pretty easy, right? So that was the third one. Let's look at another problem. Right. Question number 4. We have let complex numbers z and w satisfy mod z equals to 3 and z plus w conjugate multiplied by z conjugate minus w is equal to 7 plus 4i. We have to find the modulus of z plus 2w conjugate multiplied by z conjugate minus 2w conjugate. Okay. Now we have 7 plus 4i is equal to, if you expand this bracket, you will get z conjugate becomes mod z square minus w conjugate becomes minus mod w square. We get a plus, we get a minus zw plus, and we get a minus z conjugate w conjugate. This is what we get after simplifying. And now we know that real part of zw minus zw whole conjugate is obviously going to be 0. The real part of this is 0. Because if this is x plus iy, this is x minus iy. So when you subtract, x will get cancelled, right? It will be a purely imaginary number. So therefore, what we have is this part is purely imaginary, while this part and this part is purely real. So we can immediately say that mod of z square minus mod of w square is equal to 7. And zw minus zw whole conjugate is equal to minus 4i, right? So since we are given mod of z is 3, so this becomes 9 minus mod of w square is 7. So mod of w square is 2. We get this. And now we know this thing, right? So what do we have to find? We have to find the modulus of this. So let's evaluate what this is, what complex comes here. So that will be basically mod z square minus 4 mod w square minus 2 zw minus z conjugate w conjugate. So think about it. Mod z square is given 9 minus 4 into mod w square is 2. This is minus 2 times. This is minus 4i as we have discovered. The complex number that is coming is 1 plus 8i. 1 plus 8i is the value of this complex number. So its modulus is basically simply root 65. So again, here we use the property that a complex number, and if you subtract its conjugate from it, the real part of that is obviously 0, right? And then we are doing basic operations and simplifying, right? The next one is more interesting. The question says, given 8 non-zero reals, A1, A2 till A8, prove that among the following 6 numbers, among the following 6 numbers, and what are the 6 numbers? They are A1, A3 plus A2, A4 and A1, A5 plus A2, A6 and A1, A7 plus A2, A8. Next one is A3, A5 plus A4, A6. Next one is A3, A7 plus A4, A8. And the last one is A5, A7 plus A6, A8. Among the 6 numbers, we have to prove that at least one of them is non-negative. Non-negative. So the question seems a little strange. You have to think creatively and think of a good construction by which you can do this. So think about it. Let's assume we make 4 complex numbers. Let's basically construct 4 complex numbers. And these numbers are Z1, which is A1 plus A2i, Z2, which is A3 plus A4i, Z3, which is A5 plus A6i, and Z4, which is A7 plus A8i. We have made these 4 complex numbers. Now let's calculate what is the value of mod of Z1 minus Z2 square. So I'll do that in the next screen. Mod of Z1 minus Z2 square. What is this modulus? This is going to be A1 minus A3 whole square plus A2 minus A4 whole square. So that becomes equal to A1 square plus A2 square plus A3 square plus A4 square minus twice of A1 A3 plus A2 A4, right? So this can be written as correct. This is what we have here. Now, what I can do here is A1 square and A2 square. What was A1 square plus A2 square? That was equal to actually mod Z1 square, right? And A3 square plus A4 square was actually equal to mod of Z2 square. Why? Because remember our complex number. Z1 was used with A1 plus A2i. Z2 was with A3 plus A4i. Z3 was A5 and A6i. And Z4 was A7 plus A8i, right? These were the 4 numbers that we had created. And now I'm calculating mod of Z1 minus Z2 whole square. And that is coming out to be this. First, I calculated Z1 minus Z2, that will be A1 minus A3 plus A2 minus A4I, and the modulus of that is this. And then we can see here that mod of Z1 minus Z2 whole square is equal to mod of Z1 square plus mod of Z2 square minus 2 times A1 A3 plus A2 A4, right? So therefore, 2 times A1 A3 plus A2 A4 is equal to mod of Z1 square plus mod of Z2 square minus mod of Z1 minus Z2 square, right? Great. And similarly, you can write relations for all of these complex numbers. You can write exactly identical relations. This is the equation 1. You can write an equation like this. 2 times A1 A5 plus A2 A6, 2 times A1 A7 plus A2 A8, and 2 times A5 A7 plus A6 A8 will be equal to, you can show that this will be mod of Z1 square plus mod of Z3 square minus mod of Z1 minus Z3 whole square. This is equation 2. And this will be mod of Z1 square plus mod of Z4 square minus mod of Z1 minus Z4 square. This is the third one. And finally, this one is mod of Z3 square plus mod of Z4 square minus Z3 minus Z4 whole square. These 4 equations will come by simply using our complex numbers and calculating these mods, right? Now, why am I doing all this? Now, I will introduce a geometrical understanding of these. So keep in mind these equations, and we'll now do a little bit of geometry. So let's say we have our origin here, and we have Z1 here, and Z2 here. I'm making arbitrary points, Z3 here, and Z4 somewhere here, let's say, right? So we know from the vector notation, we know basically that this is your mod Z1, right? This distance is mod Z1. This distance is mod Z2. And this distance is mod Z1 minus Z2, right? So if this angle here is alpha, you can say cosine rule cos alpha should be equal to mod Z1 square plus mod Z2 square minus mod Z1 minus Z2 whole square by twice of mod Z1 mod Z2, right? So cos alpha is equal to this thing. And now if this thing is positive, the numerator is positive, the denominator is also positive, and cos alpha is positive. Now, cos alpha is positive means angle is between in the first quadrant or the fourth quadrant. And we will not be dealing with the fourth quadrant so much because that will be angles above 3 pi by 2. So what we'll say is angle is alpha should be acute, right? Basically, if this quantity is positive, the cos alpha is positive, and therefore the angle is acute, right? Now, similarly, all of these angles will be beta and then gamma and then finally delta or something. All 4 equations that we had formed basically mean that the twice of A1, A3, twice of A1, A3 plus A2, A4, that was equal to mod of Z1 square plus mod of Z2 square minus mod of Z1 minus Z2 whole square. And this quantity is actually twice of mod Z1 mod Z2 into cos alpha, right? Now, assume for a moment, for contradiction's sake, that all of them are negative, right? We have to prove that one of them is non-negative, right? That was our question. Out of the 6 numbers, one of them is non-negative. So right now we are going to say that assume that all of them are negative. So if all of them are negative, then all the cos alphas are negative. Cos alpha is less than 0. That means alpha is greater than 90 degrees, right? And we have basically six angles here, right? We can definitely say, or even if you just consider the four angles here, right? OZ1, OZ2, OZ3, OZ4, right? The angle between any one of these pairs, the angle between any one of these pairs, any one of these vectors, OZ1, OZ2, OZ3, and OZ4, must be less than equal to 90 degrees. Because otherwise we can form a quadrilateral like this, and we know that this angle plus this angle plus this, all the angles are adding up to something greater than 360 degrees. If all the angles are greater than 90 degrees, you will not be able to form a quadrilateral. So basically the idea is, since each of these numbers are the cosine of the angle between the vectors, since the total number of angles around a circle must add up to 360 degrees, you cannot have all angles greater than 90 and all. Cos alpha will be negative only if the angle is greater than 90, and since all angles cannot be greater than 90, it will basically not work, right? So we have to prove this by contradiction, and we have to understand that we constructed this situation where we made four complex numbers and we were able to represent a1, a3 plus a2, a4 and all in terms of cosine rule and cos of the angle between the OZ1 and OZ2 vectors. Right? So keep that in mind. Let's move on now. The next one is this one. Let 3 points of the complex plane P, Z1, Z2, Z3, and these points are basically A, B, C in the complex plane. Suppose mod of Z1 is equal to 1, Z2 is equal to Z1 into Z, Z3 is equal to Z2 into Z, where Z is equal to 3 by 2, 1 plus root 3I. We have to find the area of quadrilateral OABC. Okay. Now notice that Z is equal to 3 by 2, 1 plus root 3I, and that is 3 by 3 times, and take the half inside, it can be written as cos pi by 3 plus I sin pi by 3, right? And let's say point A, which was Z1, since mod of Z1 is 1, the Z1 can be written as cos theta plus I sin theta, right? So when you have point P, which is Z2, point P, which is Z2, which is Z1 times Z, so that is equal to Z1 times Z is 3 times cos pi by 3 plus I sin pi by 3, which means when you do complex number multiplication, you can think of multiplication as a counterclockwise rotation by some angle, and also the magnitude of the final complex number becomes scaled, right? So here we can say that OB vector is 3 times OA vector and obtained by rotating OA by pi by 3 angle, right? In a counterclockwise sense. So what we figure out from here is that angle AOB is equal to pi by 3, and modulus of OB is 3 times the modulus of OA, and modulus of OA was equal to 1 because mod of Z1 was 1. So this is 3, right? Similarly, Z3 is equal to Z2Z, which is equal to Z2 into 3 cos pi by 3 plus I sine pi by 3. And exactly same thing happens here, and you figure out that modulus of OC is 9 and angle BOC is also pi by 3. The angle between OB and OC is also 60 degrees. So now that you know all this information, you have a situation like this. OA, this is OA, length is 1. OB is rotated by 60 degree and length is 3. And OC is even further longer. OC is 9, this is 3. And these angles are 60 degree and 60 degree. This is A. And you have to find the area of this quadrilateral, right? This is OABC. The area of the quadrilateral OABC is basically equal to area of OAB plus area of OBC, and that is equal to half into mod of OA mod of OB sine of angle AOB, which is 60 degree, plus half into mod of OB mod of OC into sine of the angle between them, which is 60 degree. And this becomes half of 1 into 3 into root 3 by 2 plus half of 1 3 into 9 into root 3 by 2. So that comes out to be 15 root 3 by 2. That is my required area of the quadrilateral. So here, basically what we are doing is we are realizing that complex number multiplication is a rotation, and it is rotation plus scaling. The magnitude of the complex number changes depending on the modulus of the number that you are multiplying it with, and the angle that the original complex number makes with the positive x-axis, that angle also changes, right? Let's look at the next one. Assume that complex number z satisfies argument of z plus 3 is equal to 3 pi by 4. We are being asked for what value of z, the maximum value of u is equal to 1 by mod of z plus 6 plus mod of z minus 3i can be obtained. It's a nice geometrical problem. So try and understand what we are going to do here. Now think about this. This says that the argument of this complex number is equal to 3 pi by 4. Given argument of z plus 3 is equal to 3 pi by 4. This basically is the ray starting from point A, which is minus 3 comma 0, and making an angle 3 pi by 4 with the positive x-axis. This is the meaning of argument of a complex number being equal to some constant. Why are we starting from minus 3 comma 0? Because we have shifted this. If the question was simply rz is equal to 3 pi by 4, I would have started from the origin. But right now it is z plus 3. So that means it is a left shift by minus 3 units, right? You can get this by simply doing z is equal to x plus iy and saying that argument of x plus 3 plus iy is basically tan inverse of y by x plus 3 is equal to 3 pi by 4. So when you do tan on both sides, you get y by x plus 3 is equal to tan 3 pi by 4 minus 1. So you're getting y is equal to minus of x plus 3. That is the equation, and notice that that is the straight line, right? So that is another way to get that idea, that this is a situation where argument is 3 pi by 4. We are not doing the other part of the line, because if you go on the other part of the line, the argument is no longer 3 pi by 4. When you come here, the argument becomes negative, right? So for positive 3 pi by 4 to be argument, you only have to take the top half of the line. So this is a ray, not a full line, right? So we know where z lies. Z lies on that ray. Now we have to think about how to minimize the value of, or maximize the value of u, right? So let's think of that. So we want to find a point Z on the ray such that U is maximized. And for U to be maximized, since U was equal to 1 by mod of Z plus 6 plus mod of Z minus 3i, that is the same thing as saying we want to make Z plus 6 plus Z minus 3i minimal, right? We want to minimize the denominator to maximize U, right? Now, what is this? This is basically sum of distances of point Z from points B is minus 6 comma 0 and C is 0 comma 3, right? So think about it. My A point was here, minus 3 comma 0. B point is here, minus 6 comma 0. And this point is, C point is here, 0 comma 3. And Z lies on this line. Z lies on somewhere on this line. And this is my Z. So distance here and distance here. I want to do minimum of this and this, right? I want to minimize these two distances. So now it is obvious that the sum of two distances, BZ plus CZ, is always greater than equal to BC. This is triangle inequality, right? So the minimum value of BZ plus CZ will happen to be equal to BC, right? And that will happen when Z lies on the intersection point of BC. So if you draw this BC line, that is the minimum possible distance, sum of these two distances by triangle inequality. And therefore, Z should lie on the intersection point of the line BC and the line AZ, right? So this is my required point Z, right, for minima. So you can easily find this now because equation of ray AZ is basically x plus y plus 3 equal to 0 because the slope is minus 1 and it is starting from minus 3 comma 0. Equation of BC, since 2 points are known, minus 6 comma 0 and 0 comma 3, you can write the equation of BC. It is x minus 2y plus 6 equal to 0. So the intersection point of these two is minus 4 comma 1. The intersection point of this line and this line is minus 4 comma 1. So the value of Z is minus 4 plus I, right? And at this point, the maximum value of U will occur, right? So hopefully you have understood what is happening here. Basically, we are using the geometrical meaning of complex numbers to solve this problem, right? Let's look at the next problem. So we have given a positive real number A if Z is equal to 1 by A plus Ti. Here T is a real parameter. T is a real parameter. If Z is equal to 1 by A plus Ti achieves a maximum value of 2 for mod of Z minus I, find A. So what he is saying in the problem is uh, mod of Z minus I's maximum value is 2, right? So let's think about that. We have mod of Z minus I's maximum value is equal to 2 and Z is basically this. So we have to find A from there, right? So let's calculate Z minus I here. Z minus I will come out to be 1 plus T minus AI by A plus Ti, and that can be written as mod of Z minus I would be equal to mod of 1 plus T minus AI whole square by mod of a plus ti whole square. That will be 1 plus t whole square plus a square by a square plus t square. And basically, I'm saying square of the mod of z minus I, not just simply mod. Mod of z minus I whole square is equal to, if you simplify this a little bit, you can write it as 1 plus 2t plus 1 by a square plus t square. I have taken the a square and t square here and made it 1, and the remaining terms are this, right? And we know that mod of z minus I whole square is equal to 4. Z minus I max value was 2, so this max value is 4. So this is happening. So max value of 2t plus 1 by a square plus t square must be 3, right? Then only this is happening. So let's think about this now. We have maximum of 2t plus 1 by a square plus t square is equal to 3. Let's say let u is equal to 2t plus 1, and we have basically u is positive here. So we will get 2t plus 1 by a square plus t square can be written as u by a square plus, instead of t, I will write u minus 1 by 2. So this is u square minus 2u plus 1 by 4, right? Which is basically 4u by 4a square plus 1 plus u square minus 2u, right? So I can write this as 4 by 4a square plus 1 by u plus u minus 2, dividing by u up and down, right? I'm getting this, and now I will write it like this: 4 by 4a square plus 1 by u plus u minus 2. And I'll apply AMGM and say that this is less than equal to 4 by twice of root over 4a square plus 1 by u into u minus 2, which is equal to 2 by root over 4a square plus 1 minus 1, by cancelling the 2 from everywhere, right? So we are getting this. Now, this equality, this, this is less than equal to, the equality will happen when 4a square plus 1 by u is equal to u, or u is equal to root over 4a square plus 1. That is when the equality happens. And we know that this value is the maximum of this expression. So this must be equal to 3. So you'll get 2 by root over 4a square plus 1 minus 1 equal to 3. Because we know that the maximum value of this is 3. We have just taken a new variable u and we're working it out here, right? So this must be 3. So that means we get 2 is equal to 3 times root 4a square plus 1 minus 3, which means root 4a square plus 1 is equal to 5 by 3, right? And that means 25 by 9 is equal to 4a square plus 1, and we are getting a square is equal to 4 by 9, a is equal to 2 by 3 from here. So the value of a for which this happens is 2 by 3. And actually this problem is less about complex numbers and more about, can you simplify and apply AMGM properly, right? So understand that we can basically apply normal algebra stuff in your complex number questions. Uh, the next thing that we'll look at is this problem. I think it is question number 9. For given angles alpha 1, alpha 2 till alpha n, does the Thus the equation x bar n plus x bar n minus 1 sine alpha 1 plus x bar n minus 2 sine alpha 2 and so on till x into sine alpha n minus 1 plus sine alpha n equal to 0 have a complex root with modulus greater than 2 with modulus greater than 2. The question is asking whether there is a root with modulus greater than 2. So we'll say, let's say, suppose x naught is a root such that modulus of x naught is greater than or equal to 2. So we should have x naught should satisfy this equation. So you have x naught power n plus x naught power n minus 1 sine alpha 1 plus x naught power n minus 2 sine alpha 2, so on, till x naught sine alpha n minus 1 plus sine alpha n equal to 0. And now we can say that x naught power n is equal to minus of these terms. We take all the other terms on the other side, minus x naught power n minus 2 sine alpha 2 and so on, minus x naught sine alpha n minus 1 minus sine alpha n, right? And we take the modulus here, modulus on both sides. So modulus here and modulus here. So we get that mod of x naught power n, this is the whole mod. So by basic inequality, mod of z1 plus z2 is always less than equal to mod of z1 plus mod of z2 and so on, right? So therefore, mod of the sum of so many terms will be less than equal to mod of x naught power n minus 1 mod of sine alpha 1 plus mod of x naught power n minus 2 mod of sine alpha 2 and so on till mod of x naught sine alpha n minus 1 mod plus mod of sine alpha n. We have this inequality by applying standard properties of modulus. We'll simplify it on the next screen. So we have mod of x naught power n should be less than equal to x naught power n minus 1 into 1 plus x naught power n minus 2 into 1 and so on till x naught plus 1, because all the signs is less than equal to 1. The mod of all the signs will be less than equal to 1. Now this is a simple GP whose sum is mod of x naught power n minus 1 by mod of x naught minus 1, and that is clearly less than mod of x naught power n by mod of x minus 1, right? So that is less than mod of x naught power n by mod of x is 2, mod of x naught is 2, so this is 2 minus 1, which is equal to mod of x naught power n. So we are getting this series of inequalities less than equal to this, less than this, equal to mod of x naught power n, right? So ultimately we are getting an inequality mod of x naught power n is less than x mod of x naught power n, which is a contradiction. If you just focus on the first and last terms here, you cannot have a strict inequality between these two quantities which are the same, right? So that means there is no such root. There is no such root x naught such that mod of x naught is greater than or equal to 2, right? So that is basically the solution for this one. Now, the next problem that I want to discuss is basically the last one. This is the question. Let a naught, a1, a n minus 1 be a regular n polygon, be a regular n polygon. Suppose radius of circumcircle is 1, circumcircle is 1. Prove that the sum of squares of distances from any point P, from any point P on the circle to every vertex, to every vertex is a fixed value. Okay. So we know that when you have a circumcircle like this and a regular polygon of radius 1, these are roots of x power n, right? All the vertices of this regular polygon are going to be roots of the equation x power n is equal to 1. So this is the first vertex a0, 1, comma 0. The second vertex would be basically given by the second root. There are n complex roots of this equation. All of these are roots of the ai is a ith root of this equation, right? So here coordinates of a0 is 1, comma 0, and corresponding ai would be the eith root, which will be cos of 2k pi, or I can say write it as ak instead. So we'll say ak is equal to the ekth root, which is equal to cos of 2k pi by n plus I sine 2k pi by n, where k goes from 0, 1, 2 till n minus 1. If you put 0, you will get this root a0. If you put n minus 1, you will get the last vertex here, right? Now, let the corresponding point P be Z, and we know that mod Z is equal to 1 because Z lies on the circle. Now, what we have to find is sum of k goes from 0 to n minus 1, the distance of P to any of the vertices, P, A, K, mod of this distance square, right? We have to find the sum of squares of distances from P to all the vertices of the circle, right? So we'll do it on the next screen. So we need this summation mod of PAK whole square. So that is basically summation k is equal to 0 to n minus 1 mod of z minus ek whole square. That is equal to, we'll use the property that mod z square is equal to z into z conjugate. So this is like this, ek conjugate. And now we'll simplify this a little bit. This is mod z square minus z conjugate ek minus z ek conjugate plus mod ek square. So this is 1 minus z ek conjugate minus z conjugate ek plus 1, right? So you have a summation of k goes from 0 to n minus 1, 2 minus z ek conjugate minus z conjugate ek, right? Okay, so now this will become 2n minus z comes out of the summation because summation is over k, and it is summation of k goes from 0 to n minus 1 ek conjugate minus this is z conjugate comes out of the summation k goes from 0 to n minus 1 ek, right? Now the standard property is that the sum of all the roots 1 plus e1 plus e2 till en minus 1 is always equal to 0 because these are roots of this complex number. By Vieta's relation here, the sum of the roots is 0 because the second term is missing, right? So this summation is 0 and this summation is 0 because if the roots are adding up to 0, the conjugate of that will also add up to 0. right? So basically you're getting this summation is equal to 2n. So what we are getting is that the sum of squares of distances from a point P to the vertices of a regular polygon is always equal to a constant value, which is 2n, as long as the point P is on the circumcircle of the required regular polygon. So here we are proving a nice geometric result using the methods of complex numbers. Hopefully you've learned something from this video. There are more problems that I will share. That there is an assignment that comes with the lecture that you can uh, try and understand and try and attempt. And in the next videos, we'll start a new section. This was just a quick primer on complex numbers, and we have mostly discussed all of the topics that are required. Now it's about problem solving, and I'll share some assignments on this with you soon. So that's it for this video. I'll see you next time.